All right, welcome back, chemistry students, to our next video on covalent bonding. And we're going to be talking about the wonderful world of hybridization in this one. So first and foremost, when we talk about carbon, at first glance, we think that carbon should only be forming two bonds. But in actuality, it's going to form four of these hybrid or equivalent orbitals from that single s orbital and then three p orbitals all overlapping together.
Question: why would we think it would only form two bonds?
Well, if you go way back in time and do one of those orbital diagrams, the arrows, right? Aufbau, Hund's rule, up, 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 down, 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 and so on, you're going to see that carbon really only has two unpaired electrons in its valence energy level. And that would indicate, at first glance anyway, to me, that carbon really only has the ability to form two covalent bonds.
Okay, so there'd be no way for carbon to get its octet to fill up its outer shell, and we know carbon really wants to do that because it has four valence electrons, would like to get four more, could easily get to eight. So this whole hybridization process is going to happen.
So with this process, when it's forming those four hybrid orbitals, that hybridization, we're going to call that sp3 hybridization. And that allows that carbon to form those four bonds when necessary, so that it can fill up its outer electron energy levels and those valence electrons to fill that octet rule.
Alrighty, so this is a diagram of how that would come about. sp3 hybridization, you know, chemists are not very creative when it comes to naming this, so it's an S merging with 3p orbitals. And you may know a little bit about hybrid cars, where they have two different fuel supplies that are powering the car, or hybrid plants, since there's a lot of that hybridization that goes on in the orchards out here in Chesterland, and we can blend characteristics of two similar but different things together to make something more desirable.
Right.
Well, our s orbital merging with the p orbital allows for then four places where carbon can bond. And since it's one s with three p's, we call that sp3 hybridization. And then, Mr. Sustin, what kinds of bonds are forming from those hybrid orbitals?
Well, carbon's going to be able to create four different single bonds to four different atoms. And those single bonds are actually going to be sigma bonds, which are bonds that lie along the bond axis between carbon's nucleus and whatever it's bonded to. So you end up with the orbital overlap occurring along the bond axis.
And then the shape of this, and the diagram here doesn't really show that, but when you merge that sphere-shaped orbital with the p-shaped orbitals, they kind of look like bowling pins. You've got one lobe that's smaller and one lobe that's much bigger, so it looks like it's trying to be a p-shaped orbital, but with one fatter end from the s orbital kind of merging together there.
Well, it's a hybrid.
Right.
Yeah. This starts to get a little more crazy when carbon doesn't have to bond to four different things. If carbon is only bonding to three different atoms, then it only needs to make three hybrid orbitals, and one of those p orbitals keeps its original peanut shape.
All right, and that will change the plane and change the shape of this molecule. We're referencing the green orbitals here as the hybrids. They're called sp2 because they came from an s and two of the 3p orbitals. And that last p orbital, say we have two of these carbon atoms bonding together, which happens a lot in organic chemistry, those p orbitals will bump into each other and kind of take up a lot of space and leave this kind of sort of oval or circular shaped orbital that just comes from the p's bumping into each other, but still allowing for three places for carbon to bond directly.
And here we have another one of those occurring, but a little different than the last one. Instead of the sp3 or the sp2, now I have an sp orbital bonding together. So again, in this case, when we looked at the last one, we had even less places for the hydrogen to bond. Here again, I'm creating only two places, well, one place on opposite ends of those carbons for the hydrogens to bond as well in those orbitals. And again, you get some crazy things happening. We're creating even more of that overlap with those p orbitals, 2p orbitals in this case, bonded with the sp to create those bonds.
It's very difficult to imagine in three-dimensional space, but you have the hybrid orbitals are reaching across towards each other, forming a sigma bond, and then that sigma bond actually takes up all the space along the bond axis. So the unhybridized, here in this picture, they're purple, the unhybridized p orbitals have to reach out and around that bond axis. So some of those p orbitals are actually reaching up and around to connect the nucleus, and the other ones are reaching across this way in front and in back. It's very spatially, for someone who's spatially challenged, it's very hard to picture.
And we'll be talking about this in class too, and it is hard to diagram this and show you kind of in 3 dimensions what it's really going to look like. But when Mr. Sustin was referring to the bond axis, think about when our ball and stick model kits, that's where the sticks are joining the 2 spheres together, that direct overlap of a bond between atoms that you're more familiar with. And then the reason we have double, and in this example triple bonds, is because of those leftover p orbitals that didn't have to hybridize, that are not along the direct bond axis, just kind of joining together and still being able to hold valence electrons. Thank you so much for watching this segment, and we have, I think, just one to go.
More.
And remember to respond to your homework on your either Moodle message or Moodle journal. Bye.